First, happy Vijaya Dashami and happy Lokhi Puja. May Goddess Durga bless you with all that you have wished for an auspicious festival of Dashahara. May you success in removing evil from your life. So, happy Vijaya Dashami and happy Lokhi Puja again. Today, I will see new topic. In my previous video, I have discussed for a metric space XD, compact always implies sequentially compact. In my previous video, I have seen in metric space compact and sequentially compact, this condition is if and only if condition, and sequentially compact imply always limit point compact. This is I will see in my next video what is the limit point compact. In my previous video I have seen compact always implies sequentially compact, and this is the if and only if condition. Today I will see compact always imply complete, and this condition is only true for this part. Complete always does not imply compact. Compact imply complete, and this is true because in metric space compact always imply sequentially compact, and sequentially compact mean this is complete. Why? Because let xn be a Cauchy sequence in the metric space XD. It's sufficient to xn has a convergent subsequence because since the metric space is sequentially compact means it has a convergent subsequence, and since Cauchy sequence has a convergent subsequence, that means obviously the metric space XD is complete. Therefore, compact imply completeness, and this is true for sequentially compact because in metric space compact and sequentially compact, this is if and only if condition. But completeness not imply compactness. As for example, Rn with respect to usual metric, this is the complete metric space. But Rn with respect to usual metric, this is not be a compact metric space. Okay, I hope my all viewers have understood. Today's topic is, today I will see totally bounded. The relation of totally bounded is compact imply always totally bounded, and this is because compact implies sequentially compact. This is if and only condition, and sequentially compact imply totally bounded. What is totally bounded? This is today's goal of this lecture. Totally bounded is different from bounded. We all of us know in Rn compact imply closed and bounded. This is true only for Rn, otherwise this is not true. Closed and bounded, this does not imply always compact, only true for Rn. But in metric space compact always imply complete and totally bounded, and this is if and only if condition. That means in metric space compact imply sequentially compact, this is if and only if condition, and if a metric space is sequentially compact, this is always imply complete and totally bounded. If a metric space is complete and totally bounded, then the metric space always be compact. and totally bounded is different from bounded. What is the difference between bounded and totally bounded? This is today's goal of this lecture. Let's see what is the totally bounded. Metric space XD is said to be totally bounded if for any epsilon greater than 0, there exists the point x1, x2 up to xn in the metric space X such that x equal to bx1 epsilon union bx2 epsilon up to union bxn epsilon. That means X is covered by this finite ball. Any metric space is covered by union of finite ball. Then the metric space is said to be totally bounded. That means totally bounded means a metric space is covered by finite number of ball. So, in the definition has used for any epsilon greater than 0. Now I will see some example which is totally bounded or not. First example, consider X be an infinite set with discrete metric space. Obviously, the space X is not totally bounded because consider epsilon equal to half. And suppose X is totally bounded, then for any epsilon equal to half, there exists a point x1, x2, xn in the metric space X such that X equal to union of this ball B of x1 half, union B of x2 half, union B of xn half. But in discrete metric space, obviously, the ball B of x1 half means only singleton set x1. B of x2 half means singleton set x2. B of xn half means singleton set xn. That means here x imply x1 union x2 union xn. But notice here I have considered X is infinite set with discrete matrix. But here I have got only X contain only finite number. Therefore our assumption is wrong assumption. If X is infinite set with discrete metric space, then X cannot be totally bounded. This is example which is not totally bounded. Now I will see one example of totally bounded set. Close interval 0, 1. Now I will say close interval 0, 1 is a totally bounded set. Why? Because consider epsilon be any arbitrary number and partition close interval 0, 1 such type 0 equal to x0 less than x1 less than x2 up to xn equal to 1, and the ball is such type absolute value of xi minus xi plus 1 less than epsilon, where obviously I lies between 0, 1 up to n minus 1. Then obviously close interval 0, 1 is union of this ball I equal to 0 to n b of xi comma epsilon. That means obviously this is 0, 1 and 0, 1 is covered by this type of interval. So that imply closed interval 0, 1 is totally bounded because closed interval 0, 1 is covered by finite number of ball. I hope my all viewers have understood why closed interval 0, 1 is a totally bounded. Totally bounded that imply always the set is bounded, but bounded does not always imply the set is totally bounded. A totally bounded metric space is bounded because given X is totally bounded, and we have to prove X is bounded. For this, consider epsilon equal to 1 Since given x is totally bounded, that means there are x1, x2, xn in the metric space X such that X equal to union of this type of ball B of x1, 1, union B of x2, 1, union B of xn, 1. And since the ball B of x, r is bounded, so we all of us know finite union of bounded set is always bounded. So obviously since this is the finite union of bounded set, so obviously this is bounded. So our given metric space X is bounded. The converse of the above theorem is not true. Bounded not imply totally bounded. As for example, X is infinite set with discrete metric space. Obviously, X is bounded because discrete metric space, distance between the point always less than equal to 1. So obviously this is bounded. But few minutes ago I have seen when the space is infinite, then this is not be totally bounded set. This is example of metric space which is bounded but not totally bounded. That means discrete metric space is totally bounded when the set only be finite set. Okay? OL. I will say Cauchy criteria for totally bounded set. What is the Cauchy criteria of totally bounded set? Let X be a metric space. Then XD is totally bounded. That implies every sequence in XD has a Cauchy subsequence. That means totally bounded means every sequence has a Cauchy subsequence. Means if Xn be a sequence in the metric space XD, then obviously there exists a subsequence Xnk of Xn such that this subsequence be a Cauchy sequence. The theorem is every sequence in XD has a Cauchy subsequence, and the proof is such type. Assume that every sequence Xn in X has a Cauchy subsequence, and we have to prove the set X is totally bounded. For this, consider epsilon greater than 0 be given, and consider the point x1, x2, xn belongs to X such that X equal to b1 bx1 epsilon bx2 epsilon union b of xn epsilon, and choose x1 be the member of the metric space X, and if x equal to b of x1 epsilon, then obviously X is totally bounded. And if x not equal to b of x1 epsilon, that means from this condition that imply choose x2 belongs to x omitted b of x1 epsilon, and by this expression this imply d of x1 x2 greater than equal to epsilon, and if x equal to b of x1 epsilon union b of x2 epsilon, then obviously X is totally bounded. Not choose, that means if x not belongs to b of x1 epsilon union b of x2 epsilon, then choose x3 not belongs to x omitted with b of x1 epsilon union b of x2 epsilon, then obviously that imply d of x3 x1 greater than equal to epsilon and d of x3 x2 greater than equal to epsilon. Proceeding in this manner, we have to end this process at the finite stage. X equal to b of x1 epsilon union b of x2 epsilon union b of xn epsilon, and if x not equal to b of x1 epsilon union b of x2 epsilon union b of xn epsilon, then always I will construct a sequence xn in xd such that distance between xn and xm would be greater than equal to epsilon. Therefore, xn cannot have a Cauchy subsequence. That means there exists n belongs to natural number such that d of xn1 comma xn2 less than epsilon. This cannot possible. That means our assumption every sequence xn in x has a Cauchy subsequence. This would be wrong assumption. Therefore, obviously the metric space xd is totally bounded if every Cauchy sequence has a Cauchy subsequence. Okay? Well. Next result, when a metric space is sequentially compact, then that implies the metric space always be totally bounded. And I hope my all viewers have understood why sequentially compact imply the metric space is totally bounded. Because sequentially compact means we all of us know it has a convergent subsequence, and if x be a metric space and if xd be totally bounded, then sequential criteria of totally boundedness is every sequence in xd has a Cauchy subsequence. So, if a metric space is sequentially compact, then that implies the metric space is totally bounded. Our next result, a metric space is compact if and only if complete and totally bounded. And this condition is if and only if condition. Why? This is very easy. Why compact imply complete and totally bounded? Because consider x be a metric space and consider x be compact metric space. Okay? And compact means this imply sequentially compact. X be sequentially compact. And we all of us know every sequentially compact metric space is totally bounded. Few minutes ago I have seen. That means every sequentially compact metric space is totally bounded. That means x is totally bounded. And we all of us know every sequence in xd has a Cauchy subsequence. Then every sequence in xd has a Cauchy subsequence. And since the metric space x is a sequentially compact, then that implies every sequence in x has a convergent subsequence by above result. Therefore, since bisequentially compact, I have got every sequence in x has a convergent subsequence. So obviously the metric space xd is complete. So if x is compact, then in metric space compact means this is always complete and totally bounded. That means I hope my all viewers have understood. Metric space compact means sequentially compact. In my previous video I have seen this part. And sequentially compact means obviously this is totally bounded and complete. And this condition is if and only if condition. Why complete and totally bounded imply compact? This is very easy proof. Just see any standard book. You cannot be understand the converse of this theorem in better way. Then do comments in my comments box. Okay? Well. Today I will stop here. In my next video I will discuss what is the limit point compact? Limit point compact also very important for higher study. But at first I will highly recommend you, if you don't see my previous video of compact, then at first see those video. Then today's video and next video, my next video would be so easy. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.